this problem, a DC shunt motor with armature circuit resistance is zero point 0.1 ohms. First should draw the DC shunt motor diagram. This is the armature and the field, both are connected in parallel. This supply voltage. So the armature resistance is 0.1 ohms and runs at 1600 rpm. Yes, speed is 1600 rpm. While taking an armature current of 100 amperes, yes, IA is equal to 100 amperes from 230 volts DC source. This the supply voltage is 230. V is equal to 230. The current drawn from the supply is line current. The current flows through armature is armature current, and the current flows through shunt field winding is ISH, and the shunt field winding resistance is RSH. The friction and windage loss is 300 watts. So friction and windage loss, friction and windage loss, these are called the mechanical losses. Friction and windage losses is equal to 300 watts. So we can say that it is also called as the rotational losses. And the core losses are 1200 watts. The total I square R loss is 2500. Yes, total I square R loss is 2500 watts. No load core losses is 1200 watts. Find the back EMF. EB is equal to V minus IARE. What is V? 230. What is IA? The armature current is given as 100 amperes into resistance is 0.1. Armature resistance is 0.1. Then I got it as 220 volts. The power output, our gross mechanical power output is, we know that formula EB into IA, that is 220 into 100, that should be equal to 22 kilowatts. Find out the total losses. Okay, and total losses means you add all these 300 plus 1200 plus 2500, that should be equal to 1500 plus 4000 watts. So this power is called the gross mechanical power. This power is called the gross mechanical power. From this gross mechanical power, if you subtract the rotational loss minus no load core loss minus stray losses, then I will get the shaft power, that is called the useful power. The shaft power is equal to 22,000 minus 300 minus 1200 minus 0.01 times of P output. What is the stray losses is given? The stray losses E is given as 1% of the output power, that is called the useful output power. So that's why 0.01 and P out. So this is a P output power. So P output is equal to, finally I will get 20.297 kilowatts, and the shaft torque is equal to power output divided by omega. So power output divided by 2 pi n by 60. The value of the speed is given as 1600 rpm. Substitute here, then I got the torque is 121.14 Newton meter. Then the percentage efficiency is equal to output power divided by output power plus losses into 100. So 20.297 into 10 to the power of cube divided by 20.297 into 10 to the power of 3 plus 300 plus 1200 plus 202.97 plus 2500. These are called the total losses. Okay, so in this total losses plus stray load losses also missing, plus stray load losses. So substitute here, multiplied with 100, then I got it as 82.845 percentage. See, if you observe this problem, and the stray losses are equal to 1% of the output, that is also included in our total losses. 300 plus 1200 plus 2500 plus stray load losses is also there. Okay, so this efficiency is calculated 82.845. So coming to the next problem. So a 4-pole 250 volts, the number of poles is equal to 4, voltage is 250, wave connected with number of parallel paths is 2, shunt motor is power output power is equal to 10 kilowatts when running at 1000 rpm. And armature and field currents, yes, IA is 60 amperes and IF is 1 ampere. It has a Z is equal to 560 conductors. The armature resistance is RA is equal to 0.2 ohms. So brush drop, V brush drop is equal to 1 volt per brush, means we have 2 brushes. So total brush drop is 2 volts, 2 into 1. So then is calculating the back, first you should calculate the back EMF, V minus IA into RA minus V brush also there. V is 250 minus IA is 60, RA is 0.2 minus total brush drop is 2 volts. Then I got it as 236 volts. The torque which is developed by the motor, EB into IA divided by omega, EB into IA divided by 2 pi n by 60, that should be equal to 135.218 Newton meter. Shaft torque is equal to power output divided by omega, 10 into 10 to the power of 3 divided by 2 pi into 1000 by 60, 95.493 Newton meter. Coming to this SB is over, and C is equal to EB is equal to 5 Zn by 60 into P by A. So what is the flux value? We have to calculate. Flux is equal to 60 into 2 into 236 divided by 4 into 1000 into 560. That should be equal to 0.0126 Weber. And the rotational losses, how we can calculate the rotational losses? So T minus TSH. The T is called the armature torque into omega. So 135.218 minus 95.493 into omega is 2 pi into 1000 divided by 60. So 4.16 kilowatts. Then finally the line current is equal to armature current plus shunt field current. So that should be equal to 61 amperes. and power input is equal to V into IL 250 into 61, that should be equal to 15,250 watts. So power efficiency is equal to power output by power input into 100, 10 into 10 to the power of 3 divided by 15,250 into 100. So finally I got it as 65.57 percentage. So in this problem you will observe it's a very simple. The total torque means torque which is developed by the armature EB into Ia by omega. First calculate the back EMF and substitute the value, and the useful torque, that useful torque is called the shaft torque. Then Ta minus TSH will give the lost torque. The back emf is equal to Eb equal to Weiser number 60 into B by A, and the useful flux per pole. From that you can calculate the flux. The rotational losses is equal to lost torque into omega. Then I got it as the rotational losses. After that, line current is equal to Ia plus ISH. So calculate the input power, and percent efficiency is equal to output power divided by input power. Okay, thank you guys.